Seconds. Let me start from where I left it. So we're starting from this gluonic acids in expanding media and try to arrive at these qualitative features. So yeah, so in order to model the medium for different kind of scenarios, that is for the static as well as the expanding, let's first start with the basic parameter that we have in our hand. It's the quenching parameter. So for the case of the static media, you have just a simple static one, but for the, let's say for another case of this expanding, that is the exponential case, you have this exponential behavior of the quenching parameter with time, as well as for the Bjorken one, we have this initial dependence on the starting time for the quenching, this T0. And I will later stress on this value of the T0 and how it is important for our calculations and how it will, how our calculations are sensitive on this value of this T0. So let me start for these two different kind of initial Bjorken initial condition. That is one for this early quenching where you have very small starting initial quenching time, and for the late quenching where it's slightly higher than the earlier one. So we will the basic equation that we'll start with is this evolution equation that have been discussed yesterday also in different talks. So we have this coupled evolution equations which give you this quark as well as the gluon spectra inside the medium, where you have this all kind of splittings that takes place inside the medium. That is the gluon going to gluon, and this quark and the gluon splittings all taken into account through this coupled evolution equations. So the flowchart is pretty much simple. So first we will get hold of this the single parton emission spectra in this PDMPS formalism, of course, for different kind of expansion scenarios as well as for the static ones. From this single gluon emission spectra, we will categorically derive the splitting rates in the static, exponential, and the Bjorken media scenarios. And from this, we will solve the kinematic rate equations that you have over this coupled evolution equations for this quark and the gluon initiated jets. And then we will do some optimization for this to arrive at the quenching factor. And also we will impose this NPDF and the VLE phenomena to get hold of more towards these realistic values from the experiments. And finally, we will study also this rapidity dependence and estimation of electric flow for different kinds of media. So in this coupled evolution equation, what you see over highlighted here in this purple color is actually the terms that are valid only for the gluonic cascades. As I said before, for the first work is to just solve for the gluon initiated, only for the gluon cascades, which pretty much gives the basic idea of what kind of equations we are going to deal with. Yeah. So we have all the equations in place for this different kind of medium scenarios, that is the static in the limit of very soft approximations, as well as for the full static where you have this kind of this frequency dependent term also in the single gluon emission spectrum, and also as well for the exponential and the Bjorken cases. Now the thing is that if we can scale different kind of medium with each other, then it will be very good kind of approach for us, because it will help us to bypass all the complicated calculations and just to say that each and every medium are equal with each other and based on some scaling factors. So the first thing to check is that can we interpret the scalings and the different kinematical limits. So this was also stressed in earlier talk by Carlotta yesterday, like when we try to scale the single gluon emission spectra with some average value of this Q hat, which omega c is basically your half of Q hat L square. So when you take the average value of the Q hat for different kinds of media, so you see like a good semi-hard scaling in the hard part of the spectra. So I call this semi-hard scaling for different kinds of media with each other. But when you take some effective values, so basically what you do for the effective ones, you just start with this single gluon emission spectra, compute them, like take the limits in the very singular limits and try to scale them up with each other, and you have this kind of effective values for this omegas, or basically you have this effective values for this quenching parameter. So now we see that there is a nice scaling in the soft part of the spectra when you scale them up with some effective values. So this basically tells you that there is no single way of scaling the single gluon emission spectra for different medium profiles over the whole kinematical regime. So we have to just categorically segregate both of these regimes and feed them in a way. I should also stress in the slide that we have this evolution parameter defined in this way. So just take a note of this one, because we will be taking the use of this evolution parameter, which is basically the quenching function of this quenching parameter, as well as the PT and the length of the medium. Now, so we had the single gluon emission spectra. Now we try to calculate the splitting in medium splitting rates for different kind of medium profiles, and we see that when you plot them with the evolution, that is the QGP, so it's like they differ quite a lot with each other. So this dotted gray line is basically a static line. So for the static case, since the splitting rate doesn't depend on the length of the media, so you have just a flat kind of a splitting rate, which is basically a constant. But you see, like when we and this flat is kind for the soft approximation to the splitting rate. And now when we have this splitting rate for the whole static medium, that is, you don't assume any kind of soft approximations. So you have kind of this scenario, which basically at late times, it just approaches the constant splitting rate. Okay, so now we had the cases for the static media. Now what about the expanding cases? So you see, like for the exponential one, the splitting rate is just let's say just goes like exponentially over. So it says that you have a lot of splittings at late times. And for the Bjorken ones, it's like a complicated equations over there with all these Bessel's functions in this part. But I should stress that this contributions from this Bessel's part takes place in the lower evolution period. And what you see basically over this dumping of the splitting rates over time is basically caused by this prefactor, the square root of this function of this initial quenching time for the Bjorken one, which basically causes the dumping of the splitting rates at late times. So the thing is that what we should take is that the splitting rates are quite almost similar at very low formation, very low evolution time for the jet inside the medium, but you see that they differ quite a lot on the when you evolve the QGB for a lot of time. Now, what about like does they scale up properly if you use these effective parameters that I introduced in the previous slides? So okay, so when we try to do it with some effective values in the Q hat, we see that they come close to each other but not exactly match, and therefore we see that these splitting rates don't like match up with each other for the expansion scenarios with the simple static one. So what will be the consequences of this? So the first we do only for this gluonic cascades, and if we do this solve this evolution equation inside the media to arrive at this medium evolved gluon spectra. So this has been known for quite a lot of time, and there are analytical solutions for this for the static soft case for the gluon spectra. And then, but we want to go one step further. We don't want to assume any approximations inside for this in the kinematical limits, but we want to solve it like the full case. So what we see here is it like when you plug in the splitting rates for different kinds of mediums. So we arrive at a very slow quenching for the Bjorken one. So you see that when it's plotted with this momentum fraction, you see that the jet like it starts with a very high value in the x, and then it ultimately goes to the softer scale over here. So for the Bjorken one, we arrive at a slower quenching, but for the exponential one, we arrive at a very fast quenching. This is due to the fact that the splitting rates were like for the exponential case very much higher than that of the Bjorken ones. Also, we see that when we extend this and use the kernels, like the splitting kernels for the singular case in the singular limits, we see that they are like very close to each other, which basically gives you back this nice scaling with respect to this static spectra. So we say that the singular spectra, there is a nice scaling, but for the full spectra, there is no such kind of effective scaling between different medium profiles. Also, I should stress that at this low x values, we recovered this 1/√s kind of a turbulent behavior, which was first seen in the case of the static media, but we also see this kind of behavior for the other medium profiles. Now, we started with the single gluon emission spectra, we arrived in medium gluon splitting rates. So, and we then with that in medium gluon splitting race, we did the medium evolved spectra to take into account all these resummations into account to this kinematical rate equations. And when we integrate them over to arrive at this quenching of the jets inside the medium. So basically our QA is the proxy for this RA, because we are, for the time being, we are only considering the gluon contribution from the gluons and not the quarks. So we prefer to say it as QA and not RA. So it's like when we do this kind of a soft scaling, so it's in soft approximation, we do the medium profiles and resolve the equations in the soft approximations. We see that although there is a nice scaling in the soft scatter, but not like exact, but it's like a well reasonable one. But when we do some kind of optimal scaling, so that we minimize the differences with the data for the static as well as the other medium profiles, we see that there are significant differences between different kind of medium profiles. And also, like it's not possible to actually rescale this quenching factor for different media. This is our observations, I mean, or inference. And so this tells us that there is a significant difference between different kind of medium profiles. So the medium is able to distinguish like between different, I mean, the jet particle is able to distinguish between different kind of medium profiles. And we should take into account this like for different kind of medium profiles into our account for the calculations for the precise defining this kind of quenching parameters for jets inside the medium. Now, so we had this only for the gluonic cascades, but let's not limit ourselves only to the gluonic cascades inside the media. So the next natural thing will be to do is also account for the quarks inside the media. So the second thing we did was to involve in the quarks as well as the gluons inside the media, and to redo the calculations and to see what are the medium evolved spectra. So there are kind of 4 different scenarios like this. You have this gluon initiated jets. From there, you arrive at this gluon spectra after medium evolving. Also, you have this quark initiated jets from where you have this quark spectra. And these are the other terms for this quark initiated gluon spectra and everything. So what we should take from this slide is that at late times, the quarks begins to dominate the large X part of the spectra. So these qualitative features were basically observed also in the case of static media. So here we reiterate, and then we say that, yeah, we also recover this for the kind of expanding medium scenarios. So similarly, as only for the gluonic cascades, we introduce multi-partonic cascades to arrive at this RA for the jets. And we see that we recover still the differences between different kind of medium profiles. Also, we involved in additional complexities like this NPDF effects, as well as the vacuum-like emissions for different kind of media. Okay, so does the media now behave differently for rapidity? And the answer is no. So when we do the kind of a ratio for the rapidity, we say that the medium cannot distinguish the different kind of medium profiles with each other. And now, so this is, we went one step further and we calculated the V2 of the jets. And so we see that although the static and the exponential mediums after the optimizations in the Q hat are quite close to each other, but the Bjorken one is a more off with each other. So the consequence for this kind of, the reason for this kind of observation is that it is very much sensitive to the initial quenching time for the starting of the Bjorken, which is highlighted in the right-hand side plot. When you have these 2 different kind of initial starting time for the Bjorken, you see there are considerable differences between these 2 kind of medium profiles, even after the optimizations in RA. So we should say that the jet V2 remains sensitive to this initial quenching time of the Bjorken, and this was also contemporarily shown by Carlotta et al. Where they did it for this sensitivity of the V2 on this initial quenching time, but they assumed a more complex modeling of this collisional geometry, but we assumed a very simplistic model. So it's like a hard sphere model. So from there, we arrived at this kind of qualitative differences. So this is the same kind of behavior. We arrived at the V2 of the jets with PT, and so there are considerable differences of the Bjorken media with each other for this different initial quenching time. And the medium somehow favors like this early quenching time for the Bjorken. That is what we found out. Now, coming back to the third part, and this is like very much preliminary, I should say about that. So we had this single gluon emission, so we had this gluonic cascades, we introduced the quarks also into the picture, but what another ingredient we were missing is that we are missing this transverse momentum dependencies. So I will just quickly skip on this slide, is that you have this evolution equation, but this now it is written when you have this transverse momentum part into it. So when you integrate over all transverse momentum, you basically skip off this part. So it is basically integrated out, and you have this equation, which is basically your evolution equation without this KT dependency. And these equations could be solved in integral form also in a very effective way. And this has been done in the group at IIFJ by this Minkas and this TMDI's dedicated Monte Carlo programs. Okay, so the first thing is that for introduction of this transverse momentum dependency, so we start with this kind of a molar theory of multiple scattering approximation, where we segregate out the single hard scattering scenario with the multiple soft scattering scenarios. And we derived the corresponding solutions from the static media to the Bjorken expanding media. And we see that there is a very nice scaling between of the profiles with each other when we like try to see of this broadening probabilities with this molar approximations. So this kind of pushes us forward to introduce these broadening approximations to calculate the KT dependent spectra. So here are the three different schemes that we want to adapt. Is that first we take into account the medium evolved spectra without broadening, which has only this dependency in this X and the evolution time variable tau. And then we impose in this momentum broadening term to this ansatz over here. But also this is a kind of a Gaussian broadening that we assume for as the first case. And this is kind of this effective broadening that is basically this is when you take into account this molar expansion term as the broadening factor. And then also we solve the whole equation numerically, and we say that this is like a non-Gaussian broadening, where it comes from basically this sum of different Gaussians of different widths in this initial conditions, which ultimately contributes to the total spectra. So we try to see, now we have this additional sensitivity or additional parameter of this transverse momentum dependency, which we didn't have in the previous ones. And this also will allow you to go one step further to see the angular distributions. So when we compare them side by side for this Gaussian broadening case, this effective broadening or the molar case, and the non-Gaussian broadening, we see there are considerable differences with each other. So first step is to go for the simplistic state of the static media. And also we did it for the Bjorken media with different quenching times, that is the early and the late quenching. And we see that the qualitative features that we arrived for the static media are also holding for this Bjorken kind of scenarios. Now, so we also tried to see what does the distribution looks like in the KT and the X space, and we see that so in this, like when at a very high X, so you have this initial jet particle into the medium, and you see that due to these initial conditions for the broadening that are recovered over here, you see the molar kind of for the static media, you see the molar kind of a distribution at a very high X, which is basically initial condition that we imposed inside that. And this is basically transferred to each and every of the jet as you evolve, is transferred to each and every of the jets. So it's, and also for this non-Gaussian broadening over here, that you just if you just integrate it over all X and see, you just for this to see just this qualitative feature, we see this non-Gaussian broadening also in this part, as well as the rapid Gaussian kind of a broadening when you use this Gaussian broadening in this momentum broadening term. So it says that, okay, we are doing everything correct, and let's see at least at the numerical level, and let's see. So as I said, this transverse momentum dependency will allow you to get hold of the angular dependencies. So these plots are kind of very preliminary, I should say, and we were trying to look into what are exactly the quality features, so qualitatively as well as quantitatively between different kind of medium profiles. And we see that we should be like recovering, if you just go from this KT space to this angular part, we will see a large kind of particles coming in at this low X part, which is basically says that we expect different and more soft gluons at these large angles among the different medium profiles. Yeah, so this is kind of so when we plot in the in-cone energies with this angles, we see that there are some kind of differences between different kind of medium profiles when involved in for the static one for different kind of broadening approximations, as well as when we do it this different kind of so when you consider this effective broadening, that is for the molar one for different kind of medium profiles, there are also different in-cone energies for different kind of medium profiles. So one can basically estimate the fraction of this jet that is contained inside this cone size theta. So we arrived at like this, the most of the energy is still contained in the small cone, and mode is the cone energy, mode is the pattern collimated. But I should say that we need more checks on this and more analysis to conclusively say anything about this. And the work is still in progress. And we just wanted to show what's like we are doing right now. So let me summarize this. So we see that for the Bjorken expansion, the medium evolved spectra, as well as the quenching factors, are very much sensitive to this initial quenching time for the Bjorken. And it somehow spoils universal scaling features in different over the whole kinematical regime. But the rapidity dependence of the jets is very much sensitive, is not very much sensitive to this, the way kind of the medium expands. But the jet V2 is quite sensitive to the medium expansion with difference in this initial quenching time of the Bjorken. And as I said in the last plot, is that we are trying to explore this KT dependent cascades and try to arrive at this qualitative as well as the quantitative features and see what are the kind of medium profiles. I mean, make everything different with each other. So thank you for your attention. And this brings me to the last part is that we are still far away from understanding this phenomenon of jet quenching inside the expanding media. So we were somehow over here, but still there is a lot of space. Maybe it's not in a log scale, but there is a lot of space over here. And so we are more towards understanding this phenomena and open to criticism and questions from everyone. Thank you very much.
Thanks, Souvik, for the nice talk. Can you go to your slide number 8?
Yeah.
So during that rate equation, I see that you have T's and taus. That's a typo, or is a difference between T and there's D of T? Well, I guess it's all taus. It's just a type on the left hand side. Okay, but my question is, where do you evaluate the rates? So it's the same time variable for the distribution and for the rate, right?
Mm-hmm.
But I wonder if you guys consider if that's always the right thing to do, because if you go back 1 or 2 slides where you have right there. So if you look, for example, at the plot for the static rate, there are like what you see there is that it grows because that's like the formation time of the gluon. Like when you wait long enough, the rate becomes constant because it's like whatever. Yeah, because you already had time to form whatever gluon you are going to emit, and
Mm-hmm.
the rate is lower at the beginning because you still haven't for some gluons you still haven't gone through the whole formation time. But when you have the evolving medium, you have 2 competing effects. You are waiting for the formation time, but at the same time the medium is getting diluted, and that's why you never reach the rate. But then that waiting for the formation time to reach the asymptote, what's the meaning of that when you're considering a shower and each emission process is starting at a different point? You understand what I'm trying to say?
So So this tau over here is like the evolution time, like the total evolution time, like tau if so if like it's related with this total length of the media, so it's like kind of evolve everything for a particular value of tau, and you have the spectra after this.
But the fact that the rate is small for small tau is because you haven't waited long enough to form the gluons. But if when you're considering a shower, the starting time is not always the same starting time. Are you're considering the starting time like from the first parton was created, or from where the last branch was created when for your last emission?
I think from the first time it was created.
Okay, so you haven't considered if there's a change.
No. Yeah.
Okay, we can discuss more offline. Any other questions?
Can you please go back to the rapidity dependence of REA when you compare to Atlas? Could you please repeat what's the effect that you're seeing in your calculation?
Yeah, so we see, so the thing is that when we optimize different kind of medium profiles with each other for this RAA, and from there we take the ratios for different values of this rapidity, and we plot each and every profile with each other, we see that all the profiles lies on like very much top on each other. So basically there is no like the medium, there is no kind of a differences for different kind of medium profiles for this rapidity ratios.
But why do you see a rapidity dependence? What's the?
I mean, okay, so the thing is like so the answer should be for this like for this V2. So it's basically travels different kinds of lengths inside the medium, but for this rapidity. So if you see that if you just take the ratio, it's kind of lies on top for different kind of ratios. Like if I take this rapidity like for different, this is kind of this RA plot is done for this rapidity like 2.8, and so if we go for different kind of rapidities, this will also lie on top of each other. Because it is like of sensitive to the length, so but not that much to this rapidity ratios.
I would have expected the largest effect to be the steepness of the spectrum as you go to. Did you have different spectrums for different rapidities? Okay, I see. Thank you.
Yeah, so I guess just if you tune it to this one data set here, the rest are predictions somehow. Fine.
Thanks. I have actually a question to the same slide. So I mean, here you picked really the extremely high PT region, like a 360 to 500 something. But actually, and I think this is the only PT bin when Atlas can really see some significant rapidity dependence. So do you have the comparison for like some lower PT interval?
Yeah. So you were telling about this kind of PT ranges?
Yes.
No, no. Okay, so I tried also going for this lower PT ranges, but there was not much difference. So
I mean, there was no difference in your
in
model,
medium
or
profiles. Medium profiles.
Okay, thanks.
Okay. I think we should go on. So let's thank Souvik one more time.
Thank you for listening.